but it is to see what we can do about it so that the implication of a reduced availability of oil for our societies become less the source of a controversy globally in whether that will come in 5 years' time, in 10 years' time, or in 20 years' time.
And just a few words about coal and gas.
Yeah, let me say that there's one thing that's one of the details in the picture, but I would say that the forecast you could reasonably have on oil is quite different when it comes to gas. There's virtually no oil field out in the world which is not being exploited as soon as it has been found and examined, and you have done the necessary work to be able to extract the oil in a reasonably safe way and all that. With gas it's very different. There are lots of gas fields laying out there, simply waiting for a customer to come and say, "No, we would like to buy this gas." And this has been even more pronounced in recent years because, particularly in the US, something called tight gas or shale gas has caused the Americans to believe that they have much bigger gas reserves than they saw beforehand. And part of it, I'm not going into much geological detail, and I don't really know the details of it, but the best way of describing it is to say that if you have a gas field which is huge horizontally but quite thin, if you just drill down, you'll hit the gas and you can start extracting it, but because all the gas is out there, it will stop very quickly to really deliver anything. But if you can do horizontal drilling, which they can now, which they have done some years, and if furthermore you can crack by some sort of explosion or chemicals tight rock where the gas is kept, you can actually use these big gas fields, and that's what is being done for the time being, and gas has become incredibly cheap in the US. One cubic meter of gas has the same energy content as 1 liter of diesel, and 1 cubic meter of gas in the US has a price of 20% of 1 liter of diesel, before taxes and all that. In Europe, 1 cubic meter of gas costs something like 50% of 1 liter of diesel rather than 20%. So I would say that, of course, peak gas will occur at some time. Sort of conceptually, theoretically, the same problem exists with gas as with oil. But I would say this is rather 30 years after oil than 20 years after oil. I don't think anybody can give a precise number for this, but we do have, if in this country, if we have an idea that we'll be out of fossil fuels by 2050, in 40 years' time, we could actually allow ourselves to say, we don't have to worry about gas security of supply, because we'll be out of it before it becomes a problem. But we do have to worry about oil security of supply, because that is something that is going to hit us way before 2050. So depending on what time horizon you put up, if your time horizon 2100, you could say, okay, oil and gas doesn't make a big difference because at that time both will be scarce resources. But if you think about your own lifetime horizon, you would say oil is a much bigger problem than gas. Coal is a bit the same as gas, but coal is difficult from the point of view that there may be a lot of coal that hasn't really been found because the coal reserves have been so vast always that it didn't really pay to go and look for more, because I mean, if you have enough coal for the next 50 or 80 years, who would put money in to go and find additional coal that would only be useful in 80 years? So I'm not sure that anybody has a very good view of how much coal there is.
But is it true that gas is less problematic from an environmental point of view? Or?
Yeah, well, anything can be more or less problematic, yeah. but generally speaking, yes. I mean, gas has more energy per carbon atom, which basically means that it emits less CO2 per energy unit. And it particularly does it in electricity generation, because you can also produce electricity from gas more efficient than from coal. So actually electricity produced from gas only has an emission of CO2, which is 1/3 of electricity produced from coal. So on climate change, gas is absolutely a better fuel. It's also better than diesel and gasoline, but there the advantage is less, 20, at best 25%, if not so much. Gas is also a clean fuel when it comes to particulates or SO2 and the rest. Now, of course, the way you produce the fuels can have an impact on how good or bad they are. But there I would say that increased oil consumption inevitably will be more oil production in the Athabasca tar sands in Canada. I don't know whether you're aware of that. There's some awfully dirty tar sand in Canada which can be converted into oil and which creates huge pollution problems and actually also creates a higher CO2 emission because it's such a heavy oil that you have to use a lot of energy in making it into transport fuels or whatever. So there is in the whole the life cycle analysis, if you look at the whole range of activities, there's a higher CO2 emission than conventional crude oil. So I would say yes, not necessarily without exception, but in general gas is environmentally a much better fuel.
Okay, let's turn to the upper level, and here we have conversion. Now we have dig into the sources. We have conversion, distribution, storage, and use.
Yeah.
And we have subsections under these categories too, but I don't think we will go into the details. Just, I mean, if we should make the work easier for the editors, incoming editors, what would the keywords be? I mean, why do we need to know something about conversion and distribution? And
I would say that there are two things to be aware of, and that is whether you convert biomass into gasoline or coal into electricity, or electricity into hydrogen or whatever you do. All conversion processes have a certain conversion loss. There's always a loss of energy combined with this. And if you are expecting an energy sector situation where energy will be a more scarce resource, you have to be concerned about which processes are going to have high conversion losses, which are going to have low conversion losses. People say, okay, when the wind blows, you can change your electricity into hydrogen, and then when the wind doesn't blow, you turn your hydrogen back into electricity. And that's fine, that's conversion, that's twice conversion. But it turns out that the electricity you get out of that is only maybe 30 or 40% of the electricity you put into the system. That's not a particularly attractive way of doing it. If you produce second generation bioethanol, which is something you can produce from straw, it turns out that first it's only 25% of the energy content in the straw that comes out as ethanol. The rest is more or less unconverted firm biomass, firm biomass. And if you see how much energy input you need to make that conversion, because you have to boil the whole thing, you have to distill the ethanol and so on, it turns out that you have to put as much energy into the process in addition to the straw as you get out as bioethanol. So that means you have basically a conversion loss of 50% in that process. In that case, it would actually be much better to use your straw in a place where you would otherwise use natural gas, because there you can have more or less 100% utilization energy-wise. And then you use your natural gas as a transport fuel instead of this bioethanol. And you come through with a solution, an overall solution, which gives much less energy loss, much more oil substitution, much less CO2 emission than if you go into too fancy conversion processes. Electricity is one of the examples. I mean, making electricity from coal typically would give you at best something like 45% energy yield in the electricity. If you can use the waste heat from all that for domestic heating, for heating houses, then you can improve your conversion efficiency up to maybe 70 or 80%. Which is much better, and of course, which then means that you save on gas oil you would otherwise have used in order to heat your houses. And if you use natural gas for electricity, you can have efficiency rates of up to 60%. So one of the things in all this conversion talking is that be aware that an ambitious energy policy has to look very much, not just into energy efficiency or energy savings possible, but also to energy losses in the conversion processes. Otherwise, to say, of course, electricity will be a key in the future energy system in Denmark. If we are going to have 75% wind and 25% biomass, to put it in broad terms, it basically means that a lot of the energy use we have today will be in form of electricity. And that basically means that there's a challenge in both coping with an energy sector where electricity is being generated as the wind blows. I mean, we're used to have electricity supply matching our demand. Whenever we need some, we get it. Now we will in the future see that we will have to let our demand follow the supply, because the supply is there when the wind blows, and that means that you will have to find storage. You may have to find that may be with or without conversion. You will have to find ways of, for instance, running your dishwasher at periods where there's electricity available. There are a number of industrial processes where you can use electricity, not necessarily at the same level all the time. Supermarkets, for instance, can cool down their freezers or refrigerators in the late night before the morning peak in electricity demand. I mean, there are a lot of things like that come into this process of having electricity. And there's one particularly important thing in electricity in the conversion process, and that is that there is something called heat pumps. And now it becomes a bit technical, but a heat pump is, in fact, it's the opposite of a refrigerator. A refrigerator takes heat out of the internal of the refrigerator and delivers to the outside. You can do the same if you turn it around and you take some heat outside and put it in here into your room as heat via the same type of a pump as you have in a refrigerator. And this has this big advantage that you can transfer 3 times as much heat into the room as the energy content in the electricity you feed into your pump. So there in most cases you lose energy, but here is a way where you actually sort of gain energy. It's not against the first law of thermodynamics that say energy is constant, because it will be lost again to the outside through windows and doors, but you can actually move energy from where you don't need it outside to where you need it with a gain in efficiency. So that is among the possible conversion processes, electricity to heat, where you can gain. The other way around, heat to electricity, that unfortunately doesn't allow you anything like that. It's against the laws of nature. But I'm not going to elaborate further on that.
So Grundfos is doing a very important job on
there's a lot to be gained on all things that has with motors and pumps and so on.
Yeah.
And anything as simple as an electric motor can use very different quantities of electricity for actually doing the same job, depending on the design. Of course, sometimes the more efficient one is more expensive, and there's a general tendency that many both private people or enterprises are hesitant to get the money out of their pocket up front. They'll rather pay less for the equipment and then pay more at the end. It goes for people who buy cars as well. It's very difficult to sell a fuel-efficient car if it's more expensive than a non-efficient car. Yeah. So that's a whole story. I mean, I could spend an hour on explaining examples and so on, mechanisms on that. But I'm not sure we have that much time.
No, then we have the distribution.
Yeah.
I mean, it's more or less what you would expect, maybe.
Yeah, well, that's not. Well, there's one. I mean, distribution is everything. You truck oil products around. You send gas over thousands of kilometers. You ship oil from the Middle East to Japan and US and so on. So this is relatively banal. Yeah. There's one thing which is interesting. Again, all transport and distribution of energy also has an energy cost. You can't do any of these things without energy cost. But what has been developed recently is a special type of electric cable, a high voltage direct current. You know, most of the electricity we deal with is alternating current. If you don't know the difference, it'll take too much time, but ask one of your friends then to have it properly explained. But there is direct current and alternating current, and some companies have developed cables that allow transmission of big quantities of electricity as direct current over long distances with very small losses. Recently a cable has been laid between southern Norway and Holland, and I think that the loss of an electricity through that cable, which is 1,000 kilometers or something like that, is between 1% and 2%. So this is important, because if this is really going to be commercially fully viable, and it is actually, then it could be used to tie together an extensive wind energy system in Northern Europe with a solar energy system in Southern Europe, or some people are even talking about Sahara Desert Tech. There's a project that would produce